The next talk is by James Wooten. He's a professional qubit wrangler at IBM. His talk's on creating worlds with a quantum computer. Super interested today to hear about the implications of using quantum computers in the context of AI. So, James, whenever you're ready, give it a go. And I'm actually just going to read.
I think I'm currently ready. Yeah, so I actually put a different title on here, but it's all the same. So yeah, I'm James Wooten. I'm at Dikadoku on Twitter. So if you want my slides, you can actually find them if you go there. And I work for the quantum team at IBM. So IBM, you've probably heard of before. We're one of these scrappy technology startups. We only started in the early 1900s. And we have a quantum team. So we've developed a lot of different types of computing technology over the years, and quantum computing is one that we are working on. And this is something that is going to be useful for all different sorts of contexts, including AI. And for me, my own focus is on procedural generation. So I'm in a particular niche of AI, which most other people who work on AI for quantum computing aren't in. So, but that's what I'm going to talk about today, because I'm kind of mostly interested in the intersection between quantum computing and games, and that's where my my desire to look into procedural generation comes from. So I want to just give a bit of context behind that, and also explain a bit about what quantum computing is. So if you look at when computing and games first came together in the early history of computing, it was mostly people wondering what games could do for computers rather than what computers could do for games. So they were typically demonstrations of new technology or ways to educate people about the new technology or ways in which people were researching the new technology. Um, so yeah, it wasn't about what computers could bring to the game experience. Fun was not a significant consideration, and that's why there's this black and white image of a person in a suit to to represent this era on this slide. So if you look at the first steps of combining games and computers, one of them was Berti the Brain in 1950, and this was an implementation of tic-tac-toe using vacuum tubes and light bulbs. I believe it was you playing against a tic-tac-toe AI, which is of course extremely rudimentary because it's a very simple game. This was mostly done to showcase a new vacuum tube design at a trade show. So people wanted to sell their new type of vacuum tubes, and they did it to try made a game to try and impress people. And then in 1951, there was a similar thing, but this was NIM with vacuum tubes and light bulbs, so a different game. But part of the idea behind this was to illustrate the algorithm and programming principles involved. So there was an educational aspect here. People were looking into using games as a way of educating people about computers. Because at this time, I think that computing in general was probably seen as strange and arcane as normal computing, quantum computing, sorry, is now. So to ground it a little bit, make it more accessible and make it more relatable, they made a game and then explained how that game worked. And then in 1952, there was another noughts and crosses with vacuum tubes, but this time with cathode rays. So the first graphical upgrade of the computer game industry. And this was built for research into human-computer interaction specifically. At IBM in the 1950s, there was some effort to make a checkers AI. So this is, of course, much more complex than a tic-tac-toe AI, although still relatively rudimentary. So it's built to demonstrate the power of computers and to demonstrate that AI is something that exists. It was made so that it could play a reasonable game against a reasonable player. And it did fairly well at raising IBM stock price as well, which was quite good. Then in 1962, there came a game on the PDP-1. So MIT received a PDP-1, and there was a team of people who had access to it. They wanted to teach themselves how to use it. They wanted to try and work out what its capabilities were. They wanted to push it to its limit. And they also wanted to create something that was fun. So this was educational and it was a showcase, but it was also made to be fun. So this is the first game which is not just about what can games do for computers, but what can computers do for games. It gave the first novel game that you couldn't get if you didn't have a computer, unless you could make your own spaceships, because it was a game based on space battles. And then after that, there was arcade games and Mario and Zelda and all the way up to Animal Crossing, but let's not do that whole bit. So these are all based on normal computers, so digital computers. And in digital computers, information is always expressed as bits, whether it's numbers or images or music or whatever. Everything is expressed as strings of bits, which are values of 0 and 1. And if you look at any algorithm in terms of those bits, in terms of the basic bits that make up everything, everything is compiled down into very basic operations that manipulate either single bits or pairs of bits, or at least that's the way we think about it in the so-called Boolean model of computation. And then you can talk about the computational complexity, which is basically the scaling of how many of these basic operations you need to solve a given problem. And we find that there are certain types of problem which scale so badly that even for a quite reasonable seeming problem, the kind of computer you would need to solve this is a supercomputer the size of a planet running for the age of the universe, which is practically impossible to solve. Even though we know how to solve it in principle, practically we can't do that. Now, what are quantum computers? Well, they're similarly, they're digital computers. They're based on zeros and ones. We encode everything in binary, but we do that in a physical system which is governed by the laws of quantum physics, which are more general than the kind of physical laws of classical physics, which govern the way we usually encode binary information. And that just means that we have more operations that we can do on them. If you think of a single bit, then basically the only non-trivial thing you can do on a single bit is flip its value from 0 to 1, and that's it. But for quantum bits, which are called qubits, there are more things that you can do. There are more operations that you can do, even on a single qubit, because you can build up these so-called superposition states and you can manipulate those states. Now, that all sounds like superposition entanglement. When you hear about these in like Ant-Man or something, they sound almost like magic. But they're something that allow us new operations for computation in the context of quantum computing. Now, we need specific hardware to run this on, but once we do that and we design algorithms using the fact that we can compile them down into this different set of basic operations, then we'll be able to solve certain problems more quickly. Well, it means that something that would take a planet-sized supercomputer, the age of the universe, we can do in a much more reasonable time frame, like while a human is actually still alive, for example. Now, this is a technology that has been proposed in the 80s, and people have been thinking about it for quite a long time. And it's over that time we've been thinking about what kind of algorithms that we can run, and we've been developing the hardware to run it on. And now we're finally at a time when some of that hardware is available as prototype devices, and it's on the cloud. And we provide a service where you can sit at home on your laptop in your pajamas, set off a quantum job. It will go into our lab, which is represented of the two objects on the right here, and it will go into this fridge, it has a chip which is being cooled down to almost absolute zero. It's one of the coldest places in the universe, and then it runs whatever process you have and then returns it to you. So now it is possible for anyone in the world with an internet connection, which is obviously everyone listening now, to be able to run things on prototype quantum hardware. You just need to go to this URL, which is quantum-computing.ibm.com, and you could have run your first quantum job by the end of this talk. Okay, so what did I do with that once I got it? Well, I'm a researcher in the field, so the first thing I did was something scientific. But then I started thinking, well, how can I use this for games? And the first few games were still on this philosophy of what can games do for quantum computers. So the first thing I did was make a quantum version of battleships, where I basically just took the variables that you would use to encode whether a ship, how damaged the ship was, and the operations that you'd use to implement an attack, and I replaced those with qubits. You would send that little bit off to a quantum computer to calculate it. Why? Does it confer any advantage? No, but I did it because I could, and it seemed like fun. And also it allowed me to write a blog post which explained what I had done. And so it was kind of like Nimrod from 1951. I am making this to explain the algorithm, the programming principles involved. I'm trying to demysticize quantum by having not just a big complicated algorithm that looks like some alien language, but taking something that people understand and implementing that in a quantum way. And similarly, I had a game called Quantum Awesomeness, which was trying to allow people a gamified way to explore some of the constraints that we have in near-term quantum hardware, because they're not as wonderful as people have always been imagining when they imagine what will run quantum algorithms. In the past, computer scientists have always assumed that everything is going to be perfect in a quantum computer. At the moment, there's prototype devices so that there are some constraints, and this game was designed to explore those. And then in 2019, we had a game jam, and so the two games so far I've discussed were made by me. Then in the game jam, other people started making games, and one of them that ran on a real computer, a real quantum computer, was called Q Cards. It's actually a physical card game in which each card represents the basic operations of quantum computing, and by playing them, you get a sense of how they work in this more relatable scenario. And then at the end, you run it on a quantum computer to see who won. Now, a lot of other people have looked at games using the principles of quantum computing, but they always do it using a simulator. These are basically all the games so far that have used actual devices. And they've all been in this philosophy of the games are serving quantum computation somehow, usually as a way of helping us educate people or a way of showing the technology at work to help people understand it and to demystifize it. But now's the time to start looking into what can quantum computers do for games. And that is where I finally get on to talking about procedural generation. So with near-term hardware, we have to think about what it's easy for that to do because there are these limitations in what near-term hardware can do. One thing that it's easy for it to do is create quantum interference patterns. And so I have this process where I take a simple seed image and encode that in a quantum state, induce an interference process to make nice, weird patterns. So if you're in the market for weird patterns, it's basically kind of like a noise function, then this could be good for you. If you're not, then maybe not. So I have a paper on this. You can find it here, and I'm also going to give a talk about this at a conference in a couple of months, Foundations of Digital Games. And I've used this for various purposes, like I've used it to create teleportation animations based on real physics, for example. But one thing I did, and I'm showing a video of here, is I used it to create as part of a terrain generation process where the quantum interference makes a nice texture in the terrain that I generate. Okay. Then the next thing, which is the most AI related thing I've really done, which is another thing that quantum processors are good at doing, is simulating quantum processes. A quantum device that we have, quantum hardware, is a set of particles interacting in a quantum way. And if we can describe something else in that way, then we can use it to simulate that. So specifically, I thought of like a civilization-like game. So in Civilization, you've got a bunch of basically cities that suddenly decide at the same time they're going to start building nations, and they start interacting with each other. And I thought then to take the qubits of a device and use them to be the government of that nation, to encode different types of policy of the nation, like how aggressive it is or defensive it is, in different parts of the degrees of freedom of a qubit. and also different aspects of how countries relate to each other is related to the unique ways that you can get correlations in quantum state. So I'm not going into any detail of this here, but well, these are the ideas. So this means that each qubit on the device is a nation, and by interacting and by simulating interactions between these nations, we are simulating the process of them growing over time. And there's of course other details, and you can read them about them in the paper, which is at this archive. In this archive paper, and I'm also talking about it at a conference next month, the IEEE conference on games. So there's all the details are in the paper, but in any talk I have to skirt a little bit because I always have to introduce quantum computing as well, and that takes up a little bit of time. So I can't go into any more detail on that really, but just to say that we have then got this civilization type game with 53 nations whose AI is basically driven by a quantum process. So what is the place in history of this work? Like when people write the history of quantum computing, if they mention this, how will they mention it? And what I would ideally like is that they would say it's like the quantum version of space war. The first thing where quantum computing is offering something unique in procedural generation that you can't get otherwise. I don't think people will do that. I think they will most likely, if they compare it at all, they'll compare it to IBM's Checkers AI from the 1950s as an initial rudimentary implementation of an AI on a computer, but still with the philosophy of you're thinking of what can games do for quantum computers other than the other way around. And in this case, it's allowing someone from IBM to show off. Although for me, I'm not wearing a suit. I'm instead wearing some Qiskit swag. So I'm wearing some IBM Quantum swag, which you can also find. But I'll skip to that in a moment. So yeah, now's the time to start playing with quantum computing. I would say for AI, for all other kinds of things, this is you've got an opportunity now to actually use these systems. If you want to know more, the best place to get started is qiskit.org. Qiskit is the name of our software framework for quantum computing. So basically, that's what I wanted to say. And if you want to take some swag away from this conference, then here's the information you need. So yeah, thank you for your attention.
Awesome. I just screenshotted your swag because I want that shirt. I'm going to actually leave that.
This time of year, I think you should turn it into a t-shirt. That's the one I'm wearing now.
Yeah, I'm trying to pan to the audience, but I also want to keep your thing up for a minute so people can screenshot it. But everyone in the audience is clapping. Let me field YouTube for some questions. Okay, there's no question. Let's see. Questions, YouTube. Okay, so I'm wondering, like, what do you want to do next? Now that you have access to this, and all of us do, but you really know the science behind it, and you know how it works, and you know the limitations behind your system. Like, what kind of problems are you exploring now, and what do you want to build, and what, like, do you know that you want to build, but you don't think you can build yet?
Yeah. So okay, there's different eras of quantum computing that we envision, and when people were designing algorithms over the last few decades, they were envisioning something called a fault-tolerant quantum computer, and that is something that is still a decade or so away. And we're instead in this strange era of sort of discovery where theory over the last few decades hasn't prepared us for doing what we should do with the kind of devices that we have now that are a little bit imperfect. And so we can go out and we can try and find solutions. And I think maybe it's not just going to be people who have been in the field for decades, that are going to be the ones that find the best solutions. But maybe people who just come in completely from nowhere are going to be ones that give interesting solutions. We're actually running a summer school at the moment with 5,000 people attending, which is kind of amazing. And maybe one of those is going to be the first person to come up with something truly unique and useful from quantum computing. But yeah, that is the goal of everyone at the moment, to take these devices that are still in the prototype stage and find a way to make them useful for someone.
Awesome. So we have a question from YouTube, from D. They said, that was so cool. Have you started exploring this with language generation, specifically for RPG type games, but also just language generation in general? And my follow-up to this question is, are the size of the quantum computers that you have now big enough to do language generation? Like, do you have enough qubits for that?
Well, you can always do something proof of principle. In fact, there's a team at the University of Oxford, and they also work with a startup called Cambridge Quantum Computing. And the researchers at Oxford are very much based in category theory, and they have some category theoretic tools that can describe quantum computing, and they have some category theoretic tools that can describe language processing. And basically, it's the same mathematical language. So they use that in order to find ways to use quantum computing to do language processing. So I think I can't sing my own praises on this particular topic, but I think that's probably the most interesting thing that I can point people towards if they're interested in that area.
Okay, and one more quick question from June. Super cool talk. Is there already an ecosystem or app store for games, or experiments based on this SDK?
So I think Qiskit.org is the best place to go and find out what's going on, and there are places you can find out about these things. But
what was the website again?
Around. Pardon?
What was the website again?
So it's Qiskit, which is so that if you've screenshotted the swag, the word Qiskit is on there. Qiskit.
Okay, cool. Qiskit. I just put it back on the screen. Awesome.
Yeah. And the Medium blog comes up with all sorts of cool stuff. Like someone's put it on a Raspberry Pi recently. All of the games, all of the projects, that's probably the best place to find it.
All right. Well, thanks for your talk, James. It was awesome. I love hearing about quantum computing, and it's really cool to actually hear someone talking about it in terms of games. So that's the first session. It was a whirlwind session. I'm glad everything works now, and we're ready for the rest of the sessions. So now we're going to go to the first coffee break session. So on this channel, is going to be the Game of Life video art screening. So tune in. It's awesome video art that's been curated by Amy Rubenstein. Some beautiful video art, and I can't wait to watch it. Also, some of you have been invited to go to Coffee Break Islands or Coffee Break video chats, so you could go to that now. Hopefully you have your credentials for that already. And I will see you guys all back on this channel in about an hour. Don't go away. Definitely watch the video art. It's all art that's about AI and technology and the internet and how it affects everybody. And right now, these emojis are crazy. Everybody's clapping. This is so fun. I just can't believe this works, especially after everything didn't work for a while. But the video art screening is going to be awesome, and I'm going to go to that now. So see you all in about an hour for natural language understanding.